Hello everybody. Today's discussions on special electrical machines on the topic of linear induction motor. On linear induction motor, we are having a classification that is axial flux linear induction motor and also transverse flux linear induction motor. Here, both having different applications. That is, axial flux linear induction motor are having the applications of low speed applications. Nothing but while using any application on the from the motor, there you have limited nothing but low speed applications. While we are observing that the linear transverse flux linear induction motor, which is used for high speed applications, the transverse flux or field linear induction motor is used for high speed applications. This is nothing but the high speed applications, and axial flux linear induction motors are used for the low speed applications. And these linear induction motors are simple in construction, low maintenance cost. We're having so many advantages, and also that are the futures, having that high power to weight ratio, tractive effort is independent of speed. These are some of the advantages of a linear induction motor. Here, coming towards the transverse flux linear induction motor, these are used for the high speed applications. At the same time, in axial flux motor, there is a limitation on pole pitch. But in a transverse linear flux linear induction motor, there is no restriction on the pole pitch, as on flux has to be conveyed axially. That is, if you observe normal motors also, they are having that the pole pitch is to be designed differently because of due to the advantage of getting the flux, advantage of the getting the flux value or the field strength within the air gap. So the transverse linear induction motors have no restrictions on pole pitch, as on flux has to be conveyed axially. Next, if you observe here, this is the transverse flux linear induction motor single line diagram. If you observe, this is the primary and this is the secondary, aluminum secondary, and some of the steel backing is also placed. Iron backing or the steel backing, but mostly steel backing is used for the um, rust in the iron, due to a rust in the iron. So the primary is to be having with the slots, and the conductors are having within the slots of a three-phase winding, and the aluminum secondary has been placed onto the primary. This is nothing but the transverse flux linear induction motor. Next, we will observe that how the direction of the current and how the direction of the flux or the force that it can be produced from the transverse linear induction motor. From this, if you observe here, this is the direction of current of the flux, direction of current, flux and force in transverse linear induction motor. Here if you observe, the current, it should be moving like this within the conductor, and based upon the current flowing into the conductors, current direction of the current in the conductors, the flux direction is also chosen. This is nothing but the flux direction. With respect to this current and the flux, automatically the force is to be produced from the within the air gap of the induction motor. That is, the force is in a transverse nature, not in an axial manner. Axial is different and the transverse is different. So this is nothing but the transverse flux linear induction motor. The flux is to be getting in this manner and the force is to be getting in this direction. Next, the elementary relations, some of the elementary relations are shown here. That is different types of flat type and also tubular type. What we observed on the axial flux linear induction motor, in the same way, here also we are having that flat type and also tubular type. Flat type transverse flux linear induction motor and also tubular flux transverse linear induction motor. Here, individual phase cores and windings are assembled in line. If you observe here, this is the R by B with a primary, R by B with a primary, and it is nothing but the secondary plate. This is the secondary. Nothing but within the center of the particular primary, the secondary plate has been moving. That is aluminum. Here, individual phase cores. These are nothing but the individual phase cores. If you observe here, it is one first one phase core and second one and another one three phase. Again, it should be continuing. R, Y, B, R dash, Y dash, and B dash, like that. Here, individual phase core and windings with respect to core, there is a winding is also having within the core of the motor. Here, assembled in line, another type of construction is a tubular one. Okay, here these are nothing but the different types of flat type and also the tubular type transverse flux linear induction motors. Next one, here the secondary is provided with the steel backing. The secondary is provided with a steel backing. This is nothing but the steel backing. Here, this is a steel plate. Actually, this is a aluminum plate. In between this, there is a steel backing is there to reduce the reluctance of the magnetic circuit. Which is the purpose of using this steel backing is to be reduce the reluctance of the magnetic core of the circuit. And these arrangements have single slot per phase, and the successive cores are must be separated by a minimum distance to avoid axial thrust. To avoid axial thrust produced by strong axial flux distribution. How the angle axial thrust can be there with respect to the flux distribution we will observe in the next slides. Here now the successive cores must be separated by a minimum distance. These are the successive cores, means first core, second core, and another one third core RYB cores has been placed with a successive difference or a distance of a minimum value to avoid the axial thrust produced by the strong axial flux distribution. Thus, we require that axial, not the axial thrust, we require the flux distribution. Even it is an axial or even it is in a transverse flux distribution, but we require the flux distribution properly, not the flux thrust. Okay, so if you come across this, the secondary current induced by one core, the secondary current here, the secondary current induced by one core interacts less effectively with the flux of the other. Here, if you come across this, a primary is having, with respect to primary, winding is placed, that is a one phase winding, another phase, second phase, third phase, like that. Here each phase is to be giving nothing but each three phase is to be getting supply. Whenever supply is to be given, each individual successive cores produce of some flux. Therefore, with respect to this, a secondary current is also induced. Why? Because the secondary plate is running. Therefore, the secondary current induced by one core material, one core interacts less effectively with the flux of the other. Here, to increase the pole pitch value and also reduce the harmonic content, we are getting also some of harmonic values here. To reduce the harmonic content of the air gap flux, successive cores are interlinked. Those are these successive cores are also interlinked with a minimum distance value. Therefore, we reduce with interlinking nature harmonic contents. Next, this is nothing but the transverse flux linear induction motor with the core interlinking. This is the core and this is the individual, each individual cores of the RYB. Here if you observe, this is the three-phase winding with a distributed nature, short pitch distribution, short pitch nature. Here within the slots, within the uh, core of the motor of a primary side, which is given of the winding, and a steel core is to be moving inside. Therefore, this is called core interlinking. These core interlinking is having an advantage of it to reduce the harmonic content. We are getting that linear induction motor. Even for induction motor, we are getting the harmonics. Those that is also very important. Therefore, to reduce the harmonics values, here we are interlinking the core by using a steel secondary core back. Next one, thrust equation of the linear induction motor. Thrust equation of the linear induction motor here, F is a frequency of the supply voltage in hertz and tau is the pole pitch, and Vs is the synchronous speed meters per second, and V is the actual speed of runner, and S is the slip value. And next one, E1 is the EMF induced in the primary per phase, and I1 is equal to primary current. And next one, P suffix G is the gross power developed, and also P suffix M is the mechanical power developed. Pi is equal to power factor angle of the primary, and phi M is the maximum flux density in the air gap in Webers, and turns per phase. T phase is the turns per phase, and AC is the specific electrical loading, and also average magnetic loading. B average is nothing but specific magnetic loading, and L is equal to length of the field system along the direction of the motion, and P is the number of poles, and W is equal to width of the field system, and KW is the winding factor. Then we observe about this thrust equation. Here the linear synchronous speed of the traveling wave, nothing but within the air gap of the primary and also the secondary of the linear induction motor, a rotating magnetic field is produced with respect to, but it is in not in a rotating magnetic wave rotating form, but it is in a linear form. The what about the rotating magnetic field in a normal conventional induction motor is happening, but it should be happening here with a linear form. That is, a traveling wave should be produced within the air gap of the primary and the secondary. And here, Vs is nothing but the 2 tau f meters per second. V suffix s is the synchronous speed. We considered V suffix s is the synchronous speed in meters per second. But here, what is the main difference is to be, if you come across the rotating manner, the rotating speed of the linear in normal induction motors, that it should be the speed can be calculated in revolutions per minute. But here we consider the speed of the induction motors with a meter per second value. Why? Because in a linear form. The induction motor can be run in a linear form. So V suffix S is the 2 tau F meter per second, where tau is the pole pitch and F is the frequency of the supply, and V suffix S is the synchronous speed. And next one, slip. Slip is nothing but the same relation as that of the normal induction motor, that is V suffix S minus V by V suffix S. Here V suffix S is the synchronous speed and V is the normal speed by Vs. And next one, we neglect some magnetic losses and primary copper losses and how the gross power can be developed. Magnetic losses and primary copper losses. Magnetic losses and primary copper losses loss can be neglected here, and also then we're getting the gross power developed. The gross power developed P suffix G is denoted with 3 times E1 I1 cos phi, which is same as that of the normal induction motor relation only. But they we consider some copper losses, primary copper losses, and also considering some of the magnetic losses, that is core losses. Here we are not considering, here we are neglecting these those losses, and the equation is to be getting p suffix g is equal to 3 times e1 I1 cos pi value. Next one, whenever there is an EMF induced within the primary side also, as well as the secondary, they can EMF can be produced at the same time. The primary also induce some EMF with a self-induced EMF nature. So the EMF induced in the primary is also given by E1 is equal to root 2 times pi f kW winding factor, and the next one T phase turns per phase pi m value. And we consider specific electrical loading. We consider the specific electrical loading from normal electrical machines of an induction motor. That specific electrical loading is given by AC is equal to 3 into 2 turns per phase into I1 value by L. From these, we are calculating the primary current also. We are considering the primary current also, that specific electrical loading A suffix AC is equal to 3 times into 2 turns per phase. Why? Because we are getting not one turn, not one turn, it should be two turn, 2 into turns per phase into I1 value primary current by L, where L is nothing but the length of the field system along the direction of the motion, which is considered along with the direction of the motion. And the next one, I1 is equal to AC into L, AC into L by 3 into 2 into turns per phase. Also, where L is equal to P tau. P is nothing but the, here P considered as a number of poles, not the gross power developed. P suffix G is the gross power developed, and P here only P considered as a number of poles, and tau is nothing but the pole pitch value. Then the length of the field system along the direction of the motion can be considered. Then we substitute L is equal to P tau in equation I1 of a primary current value. Here the we consider the specific electric loading, and next we consider the specific magnetic loading, that is B average value. That is B average is equal to P pi m by L into W. P pi m by L into W. Then P pi m is equal to B average into L into W value. Therefore, then the B average of a specific magnetic loading is considered with that is the ratio of P number of poles into pi m value magnetic flux by L into W, where L is the number of poles into tau value into W value. Then we are getting that P pi m, we are calculating the P pi m, and by solving this, here L is equal to, the previous equation, L is equal to P into tau we observed, and then we multiplying on this L, P tau, then PB can be cancelled, therefore pi m is equal to B average into tau into W value, where W is nothing but the width of the field system. W is the width of the field system. Then by substituting the equations of E1 and I1 from the equations of 8.2 and 8.3, nothing but 8.2 and 8.3 is nothing but we know that E1 value root 2 into pi f kW into turns per phase into pi m value, and the next one I1 value, that is AC into L by 3 into 2 into turns per phase. Then we are getting that P suffix G is equal to, that is gross power developed. We know that gross power developed equation 3 into E1 I1 cos pi. Then E1 I1. E1 is nothing but this equation. Then we are substituting here the pi m value. That is pi m is equal to B average into L into W by P. We are not here cancelled. We are directly multiplied with the number of poles also. So B average L into W by P into Vs by 2 tau, where Vs by 2 tau is nothing but from the pi m equation. We are getting that from pi m equation. Therefore Vs by 2 tau into I1 value. We know that I1 equation also, AC into L by 3 into 2 into turns per phase, that is 6 turns per phase. Then the gross power developed by after substituting L is equal to P tau in equation, then we are cancelling here P and also the P value. Therefore, B average omega W by P has been cancelled. So root 2 pi into kW turns per phase and B average, and here L value can be multiplied with the P into tau value, PP cancelled. Here turns per phase and also here turns per phase are cancelled. Therefore, we are getting that pi by 2 into root 2 kW with the winding factor is there and also L value is there, W into Vs B average. Here root 2 into root 2 when we considered here. So that's why we are getting that pi by 2 root 2 value. So this is nothing but the uh, thrust of the linear force. And also we will consider that some of the expressions from this gross power developed, how the force, linear force developed. Again, some equations are there, some of the equations are there. That is, this is nothing but the gross power developed, and from this, how the linear force developed can be observed here. That is, F is nothing but the thrust force or the thrust linear force developed. F is equal to eta of Pg by Vs value. Pg by Vs value. This is the general expression which is considered from the normal force developed. That is, F is equal to eta into Pg by Vs value. Then when eta is the efficiency value, then we substituting here the gross powered equation. This gross power developed equation can be substituted here on the thrust linear force. Then we are getting that F is equal to 1.11 eta LW KW into turns per phase B average AC cos phi. Then this is nothing but the thrust linear force developed equation expression from gross power developed. And next one, as in rotating induction motor, in linear induction motor, secondary copper losses is equals to S is to Pg value. Mechanical power developed is equals to P suffix M is equal to 1 minus S into Pg value. Normal conventional induction motors having the same expressions for the secondary copper losses and also the mechanical power developed. So from these expressions of normal conventional motors, here also in linear induction motors also we're having the same values. That is secondary copper losses is equal to S into Pg value and also mechanical power developed P suffix M is equal to 1 minus S into Pg value. Then this is the expression for the thrust equations. And next one, losses. Before going to the losses, normally in a conventional induction motors, we are having rotating losses. But here, there is no rotating losses because of due to the linear induction motor. The motion of the induction motor working is to be in a linear motion. So, with respect to these, we are eliminating these rotating losses of friction and windage losses like that. And here, some of losses are there with respect to the linear induction motor. That is mainly due to these losses are not observed on the normal induction motors also, but we are observing on the this linear induction motors only. Here, those losses are called transverse edge effect and also the end effect. Edge effect and transverse end effects. Here, this is the transverse edge and end effects. Here, if you've shown, this is the primary and this is the secondary, and here also it is a primary value, or even it is a iron back. Here the primary we considering, and here it is the linear secondary. Linear secondary means it is a aluminum sheet. If you consider it is aluminum sheet, therefore how the edge effect and the end effects can be occurring. Here, if you observe, whenever the supply is to be given towards the primary, the flux is to be moving in this direction. The current is to be happening in the winding with respect to all the conductors. Therefore, with respect to the current, flux is also moving. Here, with respect to this flux, how the edge effect and end effects can be getting. Here, if you observe, the portion of the current in the secondary which has the parallel path to the direction of the motion makes no contribution towards the production of the thrust, and this current produces some losses is called edge effect. This effect is called edge effect. How the edge effect can be means, here if you observe, the portion of the current, in the secondary, this is the secondary, in the secondary which has a parallel path to the direction of the motion, and this makes no contribution towards the production of the thrust, and this current produce some losses, and this effect is called transverse edge effect. This is nothing but the transverse edge effect. And next one, end effect. Here the end of the field structure, if you observe here, this is the end and this is the end. Here we are showing with the end of the field structure on the secondary, and also go beyond the end of the structure of the primary, and hence do not contribute to useful thrust. This current also increases the losses. This current also increases the losses. Nothing but end effect of the secondary, and also end structure of the primary also. This is the end structure of the primary we consider, and this is the end one. So by with respect to these two end effects, we are not getting any thrust. So this effect is called end effect. By getting of these two effects, we are getting some losses on the linear induction motors. The transverse edge effect results in reduction of effective thrust and increase in losses. Here the transverse edge effect and transverse end effect, they can be reduced by using of increasing the number of poles with the laminations. By using number of poles means on the primary side, if you use number of poles, so number of poles means we are using a primary and secondary. So with respect to number of pole formation can be increasing, so we are reducing these two effects, end effects and also edge effect. And this is the entry and exit to transients. How the entry and exit transients can be observed. Here, in any linear induction motor, both having ends, first end and also the second end. Nothing but if you consider this is the first end and this is the second end, and like that the primary and even the primary or the secondary can be moving. Here, as the linear induction motor has ends, the traveling wave cannot join upon itself. Actually, the traveling wave cannot join upon itself on the secondary side, because they have two end sides. So this results in undesirable transients and hence lowers the performance. Undesirable transients and also lower the performance of the linear induction motor. Therefore, both entry end and exit end produce edge transients. Nothing but if you consider this is A is the entry and C is the exit one. So with respect to this A and C values, we are getting some transients. Therefore, we the primary is, suppose if you consider A and C, A, B, C has to be placed on the secondary. Therefore, The primary is assumed to be fed with AC. The primary is fed with AC. So, and produces some traveling wave magnetic flux at a velocity Vs to the right side. Nothing but to the right side means this side. Therefore, here the secondary is assumed to be moving at a velocity V in the same direction. The secondary is also moving at the same. So, with respect to this, secondary tooth A is outside. Here, the secondary tooth is outside the region where primary has no influence and carries no flux. Here, if you consider A slot is having no influence by the primary without any no flux. So, whereas B is influenced by primary. If you consider this slot is influenced by the primary and has a full flux. When secondary moves, tooth A also moves and enters the region and influence the primary. Those tooth A and A moves from C, A moves from C region having no flux to full flux. Nothing but A is empty with no flux, and but B is having flux. From A to C, there is having some flux region, and which influence the primary. So thus there comes a change in flux and hence EMF is induced. This causes the current to be established in tooth A, which is not present in other tooth. So similarly at the exit end, this is the exit end, tooth C has current during this movement. As secondary moves the entry and exit ends, teeth carries currents. This results in increased losses of the motor. Nothing but the slots is while moving the primary and the secondary. Sorry, while moving the secondary from A slot to C slot, here A has no flux, but B has flux and also C has flux. With respect to these flux influenced by the primary of the linear induction motor, A produces some current. Therefore, with respect to A of entry end and also C of exit end, we are getting some losses on the motor. Therefore, and disadvantages of these end effects, the flux distribution becomes non-uniform. First, the flux distribution becomes non-uniform, and secondary current due to end effects produce additional copper loss. Secondary current due to end effects produce additional copper loss, and the presence of flux outside the active zone results in production of retarding force, and a considerable amount of reactive VA is produced, which lowers the power factor. This is the important one while we running the induction motors. There is a power factor with a low power factor. Therefore, the power factor value of the linear induction motor, which lowers by the end effects. And within the next class, we will observe the performance equation based on current sheet concept. On next class, we discuss about the performance equation of current sheet concept. I hope all of you understand about the transverse and also the axial flux linear induction motors and also the analysis of the linear induction motor of thrust force equation. And next we observe the analysis and also the performance of a linear induction motor. Thank you.